Now I'm on air. Ladies and gentlemen, our Tech Talk 2023, the first one. The speakers, Allfred, Kevin, and Bernd, I like that you introduce yourself shortly for the audience, your company background, and that will help. So, Kevin, you are the first to start.
I'm the first.
Telling us just the company and your background. Little.
You can hear me now, so I can.
Perfectly.
Well, very good. Yeah, I'm Kevin Lenz. I'm working here in ROHM in Village next to Düsseldorf as an application marketing manager for the application e-powertrain. E-powertrain is for us everything between the battery and the motor. So I'm mainly responsible for applications, main inverter and onboard charger for xEVs. And we focus here especially on products like silicon carbide and gate drivers.
Thank you, Kevin. It's Bernd or Allfred? Who wants first? Now.
Bernd, bitte.
Allfred.
Go ahead, Bernd.
Thank you, gentlemen. Happy to be here in this meeting and happy to see old colleagues here also in the same meeting, Allfred. Pleasure to see you again. My name is Bernd Schmoelzer. I'm an application engineer for VisIC, which is an Israeli company doing gallium nitride in a direct drive configuration, and I'm within this company now for quite only half a year, I would say. And before I was part of the big company in Finland for more than a decade, and now I'm with VisIC, which is, I would say, very disturbing company. And let's talk about battery disconnect switch today.
Thank you. Now, Allfred.
Yes, thank you very much, Bodo. Happy to be here. My name is Allfred Hesener, and I'm with Navitas Semiconductor. We make gallium nitride power ICs. And in this case, we had been looking into the use for gallium nitride power ICs for motor drive applications, which represents a nice advantage. I have been around for a while, as you can probably tell from my hair color, and met very wonderful colleagues on the way, like Bernd, for example, and have spent some time with Infineon, with Fairchild, with other companies. And I'm looking forward to the very interesting discussion today. Thank you very much, Bodo.
Thank you, Allfred.
Bodo, you have to help me a little bit. I'm the only one who never worked for Infineon, and I'm here for silicon carbide, and not for gallium.
Don't worry.
Allfred, you are worried about your gray hair. I nearly have no hair anymore. A little bit the beard. So,
but it's good to see you, Bodo.
When I worked for a company which was part of Siemens, long time before Infineon was formed and taken out of Siemens. So that's a while ago. That was in the 70s. And as an application or as a design engineer at Hell, which was the Siemens company in Kiel, continuing into a marketing application job at RCA, GE Solid State, finally Harris, and ending up that Harris don't want to keep me on going because they had no power in the portfolio left. I started editorial and ended up with my magazine. That's a short form, and that's the view of more than 50 years in industry. Okay, enough of that. We have questions from the field, and we should start with the questions. Here we go. The questions to ROHM. How did this article, and we referred to the previous article in the magazine about, and how did Semicon and ROHM work together?
I think this question is for me. Yeah, thanks. Well,
of course.
Well, there's a long story behind it. I learned the last weeks or also years. And since more than 10 years, Semicon and are working together on silicon carbide solutions for XEV, for the powertrain. And you have seen some press releases within the last months, and it's now official that Semicon has qualified the newest generation from ROHM, the newest silicon carbide generation for this EM pack. And during this, let's say, qualification time, we discussed also with Semicon to make an evaluation kit ready for common customers with a gate driver, which is designed for this market, for this XEV market. And in the end, we defined a team with also Vignes Varan, Tayo Manasamy, which is our field application engineer for power and gate drivers, and Ingo Rabel from Semicon. And we make together the definition and qualification of this gate driver board, which is then used for inverter tests and double pulse tests and so on. So in the end, we wanted to have a gate driver which is quick, let's say quick and dirty, usable by customers, and they don't need to spend a lot of time to get the EM pack running. And this is how it came to this article in the end, also with some slides.
Okay, thank you, Kevin. We have to know that Semicon has mainly in that area dies from outside. They have a diode, which is well known, and they do GTO in their own fab. But all the rest, which are cell-structured design, are not part of the production at Semicon. They are all from outside vendors. Okay, we can continue to the next. So there is the questions. Are GaN switches robust enough to be used in motor drive applications? Knowing that avalanche and overcurrent robustness is different from silicon switches. We had that discussed several times in the past, and it's addressed to Navitas, to Allfred.
It's
your turn.
It's a good question.
The same question all the time.
Yeah, absolutely. If you know the weaknesses, then of course it is easier to work around and make the performance of gallium nitride happen also in motor drive applications. And that's exactly what we have done at Navitas. Our GaN power ICs include current sense, lossless current sense, which we also use for overcurrent protection. And this is able to turn off the gallium nitride switch in less than 100 nanoseconds. So in an overcurrent situation, we just simply don't let it come to the worst. We turn off the device earlier, and that deals with the overcurrent situation. And for the overvoltage topic, I think we are doing something very similar to all the other companies doing gallium nitride. We are increasing the breakdown voltage of our devices to a level where we can then safely conclude that other devices in the application will be avalanching before the gallium nitride transistor. For example, the DC link capacitor, the input rectifier, or other components. And so that gives us a very good protection of the gallium nitride transistor in pretty much all applications. The integration, of course, makes sure that this is working under all circumstances. And as a result, we have delivered now more than 70 million units to the market with 0 field failures. That's it's virtually pretty complicated actually to destroy the devices because of the very good integrated protections that we have.
Thank you, Allfred. It's
I can
also
just underline it, agree with the opinion from Allfred. So this is, VisIC is doing similar on protecting overcurrent and overvoltage. You cannot trick the physics. It's all the same for all GaN devices, and we all play the same game.
And in the battery switch, you have very high currents.
Correct. May that game change if vertical GaN comes into the arena? We now have GaN with a certain limit that's, let's say, at line voltage applications where the 600 volt is the one you target, and have a device which is 800 to 1,000, or even there are people talking about 1,000 or 1,200 volt, but they must have a breakdown at 1,800. But 1,800 breakdown is such a wide property on the IC that this will limit it, the possibilities at a certain point. So if we talk about motor control, if it's motor control in low voltage applications, I expect that GaN is a perfect device to use it. If we go to washing machines and industrial drives, it can be more difficult, but nevertheless, it can be solved. That's my view.
I agree. Achieving higher. Go ahead, Bernd.
Yeah, I don't. First of all, I must agree with Allfred before. VisIC is doing the same. If you have a breakdown voltage or if you have a nominal voltage of 650 volt, the breakdown voltage for the VisIC device, for example, is in the range of 1.5 kV. And depends on what you're targeting, Bodo. If you're talking about home appliance, if you talk about industrial drives, or like VisIC is focusing on automotive, this is differentiating from Allfred's company, which requires, in our case, lowest RDSON possible, which is clear for this high current.
Very true, very true.
Yeah.
So I think it's not so much a question of the technology base material, but rather device type. And the transistor that people are building today, the gallium nitride HEMT or high electron mobility transistor is such a powerful and high performance device, but at the same time very small and also very thin. So if you want to dissipate energy into that device, there is not a whole lot of, let's say, room to go. So you want to protect it well. And if you do that, it will deliver a wonderful performance, better than pretty much everything else. And that's what we are targeting at this point. And you may know that Navitas actually now also offers silicon carbide devices for the higher breakdown voltages. So they are very different. They are vertical devices, the classical silicon carbide MOSFETs, vertical transistors that are well known in the industry. So from a device perspective, it's a different device. And this one will handle more abuse, let's say, than the gallium nitride transistor. But the performance of a GaN, especially in the range of 600 volt and below, is really the best.
Thank you, Allfred. We have a new question coming in. Sim, salabim, saladu, saladim. Da ist sie. The question to ROHM. Can you comment on ROHM's 4th generation SiC MOSFET short circuit vis-stamp improvements? Given that modern gate drives can shut off within 2 microseconds, what is the application requirement for traction and other motor drives? That's to Kevin Lenz.
Yes, okay. So in general, the device is designed to withstand even higher short circuit times on chip level. And in the end, you need to qualify it again on power module. Of course, we cannot guarantee here for the power module. We can only make the test and the qualification for the chip, for the bare die himself. We know that there is a request of turning off short circuit within, let's say, 1.5 to 2 microseconds. And this is compared to the IGBT inverters new. So the gate driver has to withstand that. And this was also one reason why we made this investigation together with Semicon. We took the module. We didn't want to have only the bare die or the discrete components. We really wanted to test the module in short circuit conditions together with the gate driver, which is designed for this application. And here was one of the targets to find out, is the gate driver and the power module himself turning off within 2 microseconds, and what is the room here still for? So we didn't test it in this investigation, how much short circuit withstand time the module himself can provide here. So this is something needs to be discussed with the module maker, with Semicon in this time. But in general, the device is designed for even higher short circuit time. So 2 microseconds are normally, I will not say not a problem, but it's handleable, it's manageable with 2 microseconds and even higher. And one part of the test here was to make a design ready to turn off within 2 microseconds. And here we haven't seen any issue or independent from voltage and temperature range we have tested. So I hope this answers the.
Thank you, Kevin.
Bodo, please allow me to add something which is, I think, important to understand and to deepen the understanding of the technologies. What's the reason to have this high short circuit capability of SiC or IGBT? The reason is that the control loop needs this time to shut off the device. And I think, I believe, I assume that listeners here know that GaN don't have this short circuit capability. So for the GaN vendors, we have to deal this in a different way. And Navitas and VisIC are simply doing the same way, that you have a control loop which shuts off the device in the time which is below 100 nanoseconds. This is a key differentiator between the established technologies like IGBTs or also silicon carbide.
Thank you, Bernd. In general, the physics behind is that the junction temperature should not exceed a destroyable temperature, and that's part of the thermal design, how good the die is, how thin the die is, how good the heat gets extracted from the junction. That's what I learned in my life, and it was always a thematic. I remember when Infineon started to come out with the ultra thin wafer, who had a great extraction of the heat from the junction that was a benefit into all directions. That's about 25 years, 30 years ago when that started. I think ultra-thin wafers are today a standard. Okay, the next question. It's going to VisIC regarding battery disconnection switch proposed by VisIC Technologies. Is RDS on enough to handle high current and can generate less Joule loss? And what about the cost compared to SiC MOSFET for that application?
Okay, if we compare the technologies, meaning silicon carbide, silicon, and gallium nitride, it's for all the same, but the specific RDS on for gallium nitride for the same breakdown voltage would be the lowest. That means the possible achievable RDS on per square millimeter would be 0.4 million. In reality, it's not there. This is clear. This is the theoretical limit what could be achieved. Therefore, for the same area, the RDS on is much less if you compare it with silicon and even to silicon carbide. The lowest RDS on we have currently on the market from VisIC is 8 million in the first generation. And with this 8 million, we achieved in motor drive applications what we tested up to now RMS current of approximately 350 amps. So this is, from my perspective, quite impressive because this is the first time that a GaN inverter was running at this high current. And the same amp will then run through the battery disconnect switch. That means we have the proof that we have in our first generation in RDS on, which fits the requirements of the market. In the second generation, we go even lower. And this is the main differentiation from VisIC to the other companies, that we go in this depletion mode gallium nitride device, because the substrate specific RDS on from depletion mode is even lower than for an enhancement mode. So if you want to go in this direction, this is the way to go. And let's see if we can fulfill. I mean, at the end, we try to bring our devices to the lowest RDS on possible to prevent a lot of parallelization, which would be the next step. I know we have requirements, we have questions regarding 1 million switch, and we can do that. The question is, how difficult is it to achieve it by making multiple dies in parallel it's always possible, but we all know that parallelization is the last excuse you should do.
Thank you, Bernd.
Answered short notice the questions.
Okay, next question. It's addressed to all of you. Is this extended robustness regarding transient over voltage showed in datasheet? And can it be used for systematic overstress, like the spike in the flyback generated by the leakage inductance?
Yeah, maybe I can go first on this one.
Okay,
in fact, yes, the overvoltages that we see, the spikes that we see in terms of flyback circuits, also quasi-resonant flybacks, are well known since many years in the application. And we have specified our devices accordingly, and we clearly spell it out in the datasheet, actually, where there are clear definitions for both continuous DC voltages as well as transient over voltages, along with the definition of what that actually means. But in reality, what happens is that we test our devices to even higher voltages, of course, to make sure that we can fulfill the datasheet levels and limitations all the time. So the customers should not bet on it, but there is additional security in what we do.
What you normally see in the datasheet is also the output capacitance on power related and time related. And this is also reflecting a little bit these capabilities, what Allfred mentioned.
Okay. We continue. For the gun makers, Navitas and VisIC, is the lack of avalanche capability in GaN a limiter for its use in automotive motor drive applications? Can you comment on such capability? I think we had already some words on that.
I can refer to a published paper from Virginia Tech done on our 22 million device, which showed a maximum surge energy of 0.77 millijoule. In this table, which I have in front of me, this was compared to a cascode gun device and to a silicon carbide device. And for them, the surge energy was not published. And we saw that in the repetitive surge events. So let's start differently. The 22 million device has a rating of 100 amps, and we showed in the repetitive overcurrent scenario with inductive switching that we can handle 380 amps repetitive without degradation. So let's say 3 times nominal current repetitive, no degradation.
Mm-hmm. That's impressive. And I think when we talk about surge robustness, then we need to look at both current spikes and voltage spikes. And with current spikes, I think there is something that can be done, for example, turning the device off. With voltage spikes, that is not so easy. And that's what we have been focusing on with our design of the device and its high voltage robustness. But at the same time, also with the integration of the driver to have a very low inductance loop for the gate drive and make sure that we have the gate drive conditions under perfect control. And the other topic, very important to mention here, is that let's say surge conditions, single surges like we know it, for example, from qualification of grid-connected equipment, but also repetitive surges should be the exception and not normal operation. So on a normal operation, I think you will want to design the system and especially the parasitic inductances on the PCB and in the system so that surge doesn't happen. And in that context, I think motor drives are in good shape because in the typical topology that is used today with the 3 half bridges or the 6-pack or 3-phase inverter, whichever way you want to call it, there is a good way to control inductances and put additional blocking capacitance close to where the action is happening to control the spikes. Those techniques are all very well known and throughout the industry. So there is a good way of protecting the power switches so that those surge conditions usually do not happen. And the motor is an inductive load, which in that case actually works for us by making sure that the current is always cannot be discontinuous. So there can be high IDTs, yes, but from a system and application design perspective, that is an element that we can work with to make sure that the conditions are always controlled. It is much more complicated for power supplies where you are connected to the grid, where all kinds of bad things can happen. You have an AC input voltage of 265 volts, the standard voltage plus 10%, and then you have surges riding on top of that at 4 angles. That makes it really complicated to survive, for not just for GaN, but for all devices. So that's something that can only be well understood and protected against in a system context. Yeah.
Thank you, Allfred.
My comments on that is on the motor drive, we could even improve the efficiency. I think it's the same for Allfred. The DVDT is limited by the motor. And GaN switches could switch much faster as they are currently used. So this is a screw of the market. We're looking forward to see improvements on the motor side because on the semiconductor side, we are ready.
Mm-hmm. Yeah, that's very true. Still, I would like to point out that if we break down the different loss components, and here I'm thinking about not about conduction loss, but reverse recovery, output capacitance, and then what could be called overlap losses, which is the overlap of voltage and current during the switching, which is of course impacted by the switching speed. Then we can say that that particular element, the overlap losses, are the same for all 3 devices. Because the DVDT, if we choose the same DVDT for the 3 of them, then it's pure mathematics. But output capacitance and especially reverse recovery is very different for the different devices. And here we see, even at low switching speed, a strong advantage of gallium nitride over pretty much all other technologies that exist in the space. Simply, the biggest contributor here being the lack of reverse recovery, because there is no PN junction in the current flow that needs to recover when the device goes to blocking state. So that's a lot less power loss that is happening here. Unfortunately, so far, only for 650 volt and below, while at higher voltages, of course, silicon carbide is the best choice, in my opinion. And even though we have reverse recovery here, still that is a lot better than today's available silicon devices.
Thank you, Allfred. Here we go. The question is addressed to Kevin. Is there a pre-damage of the SiC MOSFET possible if the module is tested in an end-of-line test?
I think this is the question which is not so easy to answer within 1 hour discussion here. So I have to say this is a bit longer discussion, and we need to take our experts from R&D to. So I know these discussions, yes, but of course we doing our test on a way that we believe that there is no damage, and I think it's not the best idea to make a predamage in an end of line test and then ship it to the market. So the goal is always to find the test set up on a way that you test as much as possible, but don't damage your device. And this is of course in long discussion and a lot of investigations have to be done to find the right setup here.
If I may add a short comment here, Kevin, I think I'm pretty sure that you do the same thing that we do, which is doing all the high energy testing at the beginning of the test program, at which point the devices that are weaker will be destroyed. And then later on, you have all the functional tests and the parameter measurements, which will then make sure that even pre-damaged devices will not make it to the end of the test. And that way you can be pretty sure that only the good survive.
Yeah, I think the discussion was also at IGBT modules. So you're making short circuit tests, you're making double pulse tests. Is it good or is it not good? So of course we have other damages like in the silicon wafer, and yeah, I would say of course there are still some investigations, and not for every question there is an answer already, but here with our module customers, of course, we doing a lot of as much as possible tests to find exactly out is it pre-damaged or even not. And yeah, I think we have a similar test setup here.
Of course.
Okay, thank you, Kevin. It's again,
okay.
Kevin. Nowadays, some SiC players take advantage of topside cooling packages for their SiC MOSFET in automotive applications. Does ROHM has also a plan to release SiC MOSFET product with topside cooling package for better thermal performance?
Yeah. Of course, we know the trend and for topside cooled packages, and I have nothing to show today, but I can tell you that we know this trend. And the first product we are rolling out currently is some complete power module, which is in the end also a topside cooled package, but with the benefit that you have 4 devices or even 6 devices in one device. So you have we starting with the topside cooled power module instead of a topside cooled power single switch.
Okay, Kevin. Beside topside cooled means that's also bottom cooled. The top side is an additional cooling. That's what I understand.
Here's some comments, Bodo. Topside cooling per se is a very good approach. I completely agree on that, as I was doing a lot of investigations and also work in my previous company on that. VisIC is offering in the discrete device a topside cooling package, which is per se isolated. And this is, I would say, something which is worth to think through, because either the semiconductor company is taking care of the isolation or they shift it to the customer side. And as a customer, I would like to have a device which is ready to go and easy to apply. Therefore, when I joined VisIC, I was happy to see that they have an 3.5 kV rated topside cooling device.
Okay.
But Bodo, topside cooled is in general, let's say, an SMD device which is cooled on the other side, not 2 times. it's not not cooled from both sides. It's today an SMD component. You cool through the PCB, and the topside cooled is
Okay,
the other.
okay. Then it's what I had in the past was that modules or module approach had beside the bottom side also the top side thinking to cool from the top side in addition. But now it's clear, that's why I put in that question. It makes it clear that this is an SMD device that gets cooling from the top. But let me ask the question in between. SMD devices are having a certain footprint which is in general used to extract also heat. So when I think to packages like DPAC or so.
Maybe I can add a comment here. As we make GaN power ICs in QFN packages, the cooling of those devices is currently through the PCB and from there somewhere into the system. And I'm saying somewhere expressly, since that somewhere can be some cooling pad attached somewhere. It could be convection inside the system, all kinds of things that may or may not be so well under customer's control. So in order to improve the thermal design of the system and make it more reliable, I can perfectly understand the wish for a topside cooling package, because then you have you can actually implement a path with a low thermal resistance where you want it. And if I have learned one thing in those years about thermal design, it's not so much looking at the thermal resistance, but you have to watch where those calories are going and where they can go easiest. That's usually the best. And so that makes topside cooling packages actually pretty attractive. But there is a second reason that we are seeing so far our customers asking a lot, which is when the package is bottom cooled, then the thermal resistance between the chip and the PCB usually is pretty low, meaning the maximum junction temperature of the chip is limited by what the PCB can handle. And today's FR4 materials, so cost-optimized materials, they will go to 105, 110. Some customers go up to 130, but that's about it. The power semiconductors could actually handle much higher temperatures. That is not to say that customers should routinely go there and operate the devices at high temperatures. But in order to provide enough margin for abnormal system operation, it may be needed to go to high junction temperatures for braking, for a special condition, for a short circuit, or whatever it is. And that would also benefit from topside cooling, as then you have a controlled way of dealing with those higher temperatures, even if it's only for a short time. And I think that's a great advantage. And that's definitely a reason also and motivation for us to take a very deep look into the same topic.
Yeah. Thank you, Allfred.
One difficulty everyone will face, I mean, this is really now technology independent. It's only a package discussion we have now. It's valid for all of us here. One issue you will always have with topside cooling is that you have production tolerances, and this is reflected in different heights of your packages, which must be compensated via the interface. That means the interface must be always thicker than the optimum, because you will not have, or think about the topology, what you want to use. You have a PFC, you have DC-DC, whatever. If you want to make a complete application in such a way, you would like to have a common heatsink. So do you get all the devices you need in all of them in topside cooling? Currently, it's an issue, but future, hopefully, moves more towards this direction, that we can have all of them. And the question is, will we establish a standard height that maybe on the PFC stage we can use silicon carbide, and in the DC-DC we can use the gallium nitrides? This is currently open. There is no standard.
So you're talking about a standard package for all devices for silicon carbide, gallium nitride.
We have a TU220, TU247, which is a standard. Huh? If we go for a topside cooling, currently customers are facing this choice.
Yeah. That's this tolerance is also one reason why we started with the power module, because we normally go in one application where we have a 6-in-1 for the PFC stage and 2 times a 4-in-1 for the LLC phase, and then you have with the power module always 4 switches in one power module, and you always have 3 times tolerance issues or not 14 times the tolerance issue. It's also one, and it's isolated instead of a few of the topside cooled packages. Yes.
If you target applications like Allfred and VisIC is doing, motor drive, where you have the 3 half bridges, a standalone application, then it's easy. Then you have your 6 switches from the same company, everything is fine. You can exclude maybe a PFC or whatever is needed in addition. But this is easier to solve.
And it will require a good coplanarity between all those components.
Yes.
Okay, we get the next one. The question is addressed to all of you.
It goes exactly in this direction. Huh?
Yeah.
At which time frame do you see the chance that a standardized package for GaN devices will be on the market? Maybe few packages for topside cooling and others for standard bottom-side cooling.
So, will you go ahead?
Sure. That's an interesting question. At this point, it seems that some companies are kind of converging on the QFN package for bottom-side cooling. Given the fact that gallium nitride devices are usually most efficient at 650 volt and below, that immediately also points towards application with lower power. And we know 230 volt AC. Most of our houses have fuse ratings of 16 amps, which is something like 3.5 kilowatts. So that is roughly the power range where 650 volt devices are being used in large volumes. And the volume actually of these applications are the highest at lowest power and go down as the power increases. So bottom side cooling, QFN packages, I think they will be with us for a long time. For higher power, I see either more complicated PCB design coming up or more topside cooling packages. And here, I have not yet seen a clear standard emerge. That will probably take a couple of years from now until we see that. There are a few candidates. In order to really get the best out of the devices, it should be a low inductance package. And there we have to wait and see a little bit how that is progressing. Yeah.
So can you comment on the roadmap for 1.2 kilovolt devices for MV grid connected applications? For example, the cost-performance trade-off between serial connection, a lower voltage device versus a higher voltage device that may be more expensive and maybe not as efficient. Is there a big future demand for, say, 3 to 10 kV rated devices? So if we talk about 10 kV, we're at SiC.
I think, Alfred, this question is more for us.
Yeah, I think so too. Please go ahead.
Yeah, maybe I can start from ROHM view point of view, and I have to say today we are very focused on automotive applications, and that's the main focus we set today on the silicon carbide development. However, we also see other applications and have also a portfolio of upcoming power classes. And here I have to say, if there's an interest, please let us follow up privately. So I need to involve here a colleague from mine. He's especially working on industrial applications where we see even higher applications. But we have of course also a portfolio for this.
Yeah, very similar for us.
But for automotive, I have to say we don't see any 3 kilowatt soon.
Yeah. Thank you, Kevin. Yeah, same for us. We do have devices on the market at this point for 1.7 kilovolt and 3.3 kilovolt. And we even have first chip products available for 6.5 kilovolt. Obviously, the higher the voltage, the more complicated the package, and creepage and clearance distances need to be considered. Those applications are pretty special. They are not your regular washing machine or whatever it is. So other regulations and qualification requirements may be there. But yeah, the first devices are available. Actually, they have a pretty good and interesting performance and may open up easier ways of doing those designs. In fact, for the higher voltages, we have seen a lot of multi-level inverter topologies coming up, for example, serial in, parallel out, 3-level neutral point clamped, and all the different topologies that the engineers in the industry have been so inventive. And by using a transistor with a higher breakdown voltage, that can be simplified. Sometimes better, sometimes worse performance, but there is not only the performance there's also cost, system design, reliability, many different things to consider. And there is room. There will be, I think, more exciting developments coming from all the players in this industry for higher voltages. But I agree with Kevin. The big trend in EV is the move to 800-volt battery systems, and that can very nicely be addressed with 1200-volt devices, which we all have available, and good devices available. So I think that will be the main trend that we will see in the electrification of the car.
Yeah, VisIC is currently 650-volt devices, and we know the demand of 800-volt on the market. And our partners are doing exactly what Alfred just said, doing multi-level inverter of different topologies, being aware that this is more complex from control perspective. In efficiency, I have papers in hand which showing benefits. So it's always a system view which must be done. And if you talk to two partners, you have three opinions. Unluckily, it's like that. I underline that a multi-level inverter is a good approach to fulfill higher voltage ratings which are needed.
And on the other hand, you have more devices involved, and the failure theoretical can go up. The failure possibility.
If you have such tests like Navitas that you have nearly zero field failure, then the absolute failure will also result in close to zero.
Okay, we are ready for the next. Are the benefits of a fully integrated GaN IC worthwhile considering the additional design effort and qualification challenges? Many vendors seem to be taking the power stage approach of gun hems with an accompanying SiC control circuitry.
Yeah, a very good question. And in fact, I see it exactly the other way around. The integration of the driver and the gallium nitride transistor makes for a digitally controllable power stage, which is actually much easier to use. And in our case, the voltage regulator for the gate driver is built in as well, so that we have the gate drive condition under perfect control all the time. That's a key for reliability. So not to talk bad so much about the discrete GaN transistors out there, but usually when you look at the discrete GaN transistors, you get a 30-page application note how to do the gate drive. So the engineers need to spend a lot of time and work to make the gate drive so that reliability is not impacted while you get the best performance out of it. And that's not an easy task. It's actually easier to use an integrated driver where all the hard work is already done. I would like to compare this to the situation of a separate discrete gate driver and IGBTs or MOSFETs as compared to an IPM where the gate driver is integrated and all the adjustments needed to drive the power switches correctly are already done, and that makes it much easier to use.
Absolutely, Allfred. Any length of wire between the switch and the driver is sometimes a nightmare and limits the possibility of switching behavior and switching speed.
But I'm sure Bernd has something to say about this as well.
I completely agree with the opinion, Allfred, that gate drive circuitry is crucial. And I think we have a 30-page application note which is describing the gate drive. But in our case, for these high current applications, we decided to exclude the gate driving from the package to have more room of maneuver from thermal perspective.
Of course, when you are switching several hundred amps, then that's a very different story as compared to our major use cases, which are, let's say, below 1 kilowatt. So then the currents are much lower.
Yes, and in our case, we started 100 kilowatt. That's why our decision was to exclude it and to write a nice app note.
Makes sense.
Bernd, can you summarize for silicon carbide users the difference, the main difference, to summarize the 30 pages to 3 words or 3 sentences? What is important to know? What is gate voltage? What are the critical points here?
Our devices.
Yes.
As you know, that gallium nitride has normally a very low threshold voltage, depending on the technology you're using. VisIC has chosen a different solution, which is the direct drive, where we have the gun hemmed, and in series we also have a low voltage MOSFET, but we drive the gun hemmed, not like in the cascode where you drive the low voltage MOSFET. And this way how we operate the device allows us to have a gate threshold voltage of in the range of 5.56 volts, which is much more than you have from different suppliers. That means you have less risk of having a return on if your design is not done properly. And this comes back to what Allfred mentioned before, your commutation loop inductance must be ideally 0, but this is not the case. But what we can achieve is several nanohenry. Yeah?
Good. Thanks.
This is the direct drive. What VisIC is offering for the automotive market. There are also other suppliers which are doing the same way for higher RDS-on. And I know also this way of driving in the past from SiC JFET.
Yeah.
Thank you, Bernd.
Well,
We are approaching our last question for today. What kind of application do these SiC 3.3 kV, 6.6 kV, and 10 kV devices cater to apart from auxiliary power and traction inverters? Could you also talk about the demand and application for such discrete SiC devices apart from auxiliary power? Okay, it's more or less to Kevin and Bernd. I think.
well, this high voltage doesn't go to me. Sorry.
No. It's
I think 3.3 kV is for Allfred,
It's-
I have to say.
Well, I can make a few comments here. Of course, there are industrial applications, welding, plasma equipment, induction heating, and other industrial applications that may need higher voltages due to the higher power levels involved. Then, of course, traction is an important point. And here we're not talking about the electric car, but more electrified utility vehicles, trains, buses, and other higher power applications. And then energy distribution. So there is, for example, higher power solar inverter applications, wind power, and similar things that will benefit from being able to go into a higher voltage. So that's a very diversified application space. It's hard to point to the one killer application that will make 50% of the market. It's a lot of different stuff, industrial applications, for which Europe and Germany in particular is well known for, and Austria, of course.
Allfred, I have just in mind that there may be also medical applications like kidney stone destroyable systems.
Not sure. That would be a lot of power so close to the body. I think they do that with ultrasonics and
the power is
range.
the ultrasonic, but you have to have the coils and things.
Mm-hmm. Maybe. Yeah.
I remember, but that's 25, 30 years ago, that people used high voltage IGBT switches in that arena, but high voltage 1200 volt and these kind of devices at that time.
Mm-hmm.
Okay. It was a nice and fruitful discussion today, and we have a cold northern day which is quite overcasted. I can't see the sea, I can't see the beach.
You have
And normally, if I could look straight out, I see the Kiel Fjord and see the ships going in and out to the Kaiser Wilhelm Canal, which is now called the Kiel Canal. And if I look the other direction, there is not far, a few steps from here, the beach. But today it's too cold. It's around 0 degrees. And it's better if I go home later on, I wear my good, how you call it, Mütze.
Beanie. Yeah, nice. You know, when I look out the window, I see an office building.
I have worked
it's
a
all not
long
so
time
critical if
to end up here.
If I hear our colleagues in Kyoto, where it's our headquarters, they have some other issues. They had to all pick their kids from school because they had the biggest snowstorm since many years. So I haven't checked how much centimeters or meters they have, because we had some Teams issues this morning, like everywhere on the world. But they have a little bit more snow, and seems to be much colder than in Laboe.
Yeah. I remember when I was younger in 1978 and 1979, the Kiel Fjord and the Baltic Sea was frozen, and we had so much snow on those roads which connect the little village that we couldn't get in and out for 3 days. So that was the so-called snow catastrophe in 78, 79. It was around Christmas, New Year, and everybody said it will never return, and it returned in March again. That's history. Okay, gentlemen, thank you so much. And we're looking forward to the next talk, and looking forward to Holger, probably, who will be in Orlando. Will meet Holger. Holger will represent the magazine in Orlando at APEC. I will stay home, and we will personally meet at PCIM in May again.
Great.
So all the
Thank you very
best,
much, Bodo.
and not so much snow all around, only snow where it makes sense. Goodbye, gentlemen.
Thank you very much.
Thank you.
Alfred.
Bye-bye.
Pleasure to see you again.
Servus, Bernd. Yeah.
Yeah.
Same here.
Thank you.
Goodbye.
Servus.
Bye, everybody.
Bye-bye.
Bye-bye.